hands should be recording. All right, so let's start with the first homework, problem set 1. Overall, people did okay on it. There were some issues around the formulas in manipulating the two formulas. Remember, if you just want to solve for like frequency here, to get frequency by itself, you divide both sides by what?
You just need one.
What would you have to divide by?
V.
If I want to solve for V.
Wouldn't it be E
Isn't it
divided by
C
H?
over V?
Yeah, E divided by H. If I want to solve for V, divide both sides by H. Just E over H. And then the same thing over here. If I want to solve for wavelength, same thing. So for manipulating these, my little draw thing here. So if I wanted to solve for wavelength, it would be equal to C speed of light over frequency. Okay. So these are the only two equations given to you on the formula sheet. And then you're given Planck's constant, you're given the speed of light. So that's about it. I would go through the problems in the book, make sure you know what you're doing with those problems. Just work through them, the ones that are solved for you, and you should hopefully be okay with these. They don't get harder than what we did. Any other questions on these? Did we do okay with electron configurations?
Yeah.
Yeah. There seemed to be a little bit of issue with shorthand, always making sure we're starting. If AR is the end of 3, then you always start in 4S.
Oh.
Okay. So like if you write neon as your noble gas, then you would start at 3S. You start wherever your S block is after the noble gas, but you're always starting in an S block. And then for configurations that show an excited electron, it's just one that jumped from where it should be. So down here in number 5, it should have been 1s2, 2s2, 2p5, but instead that one that should have been 2p5 jumped to 3s1. So overall, good job on that homework. Last night's homework, if you turned it in last night, I returned it already to you. Any questions on this first part? We're going to go over this today. Today we're going to talk about ZF, and we're going to talk about shielding and ionization energy.
Okay.
We'll solve some problems today too. So we okay with 1, what is meant by effective nuclear charge?
Yeah.
Yes?
Yeah.
Okay. Are we okay with the pattern going left to right?
Yeah.
So the big thing with that is on the AP test, you can't just say effective nuclear charge increases going left to right. You have to be able to say why. And so you have to talk about how they have the same 4 electrons, but they have 1 more proton every time you go right. And so that proton pulls harder on the electrons and makes everything sort of come smaller. Any other questions on these? Are we okay?
Yeah.
The last ones, and we'll go over this today. Are we okay with these? Well, let's go over this stuff, and then we'll see if we still have questions, okay? So I'm going to go through some of this stuff pretty quick. And I'm going to, I'll stop a couple times. I'm going to mute everybody right now. All right. So effective nuclear charge, when we're talking about effective nuclear charge, so remember, an atom has a nucleus that has protons in it that are positive. And then around it, it has the electrons that are negative. And the reason those electrons stay there is the protons in the nucleus are pulling on them. that pull is a pretty strong force, and we call it effective nuclear charge. But to really find the true pull, we have to take into account the core electrons that are shielding it. And all shielding is sort of some electrons blocking the pull of the nucleus. It's like if you put a magnet on a refrigerator, and then you put a piece of paper between the magnet and the refrigerator, it's not going to stick as good to it because there's some shielding from that paper that's blocking the pull. And so it's sort of a similar idea there, that you just have core electrons, which we call shielding electrons, and they're essentially blocking some of the nucleus's pull on those valence electrons. And all we care about is valence electrons when we're talking about pull. So our formula for ZF is Z minus S, where Z is your number of protons and S is your core electrons. And that'll give you the actual charge that you feel. The larger the charge, the stronger the pull of the nucleus, and the more it's going to pull the electrons inward. And if electrons get pulled inward, it causes the entire atom to sort of decrease in size or have a smaller atomic radius. So if we just look going across row 2 here is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And if we look at what happens with their ZF as we go across, we see it just increases 1 every time. And the reason it's increasing 1 every time is if you look at them, they all have 2 core electrons. Neon has 2, lithium has 2. So in a row, the core electrons never change. And so as we go across, we're adding 1 valence electron, but we're also adding 1 proton every time. Lithium has 3 protons, 4 protons, 5 protons. And remember, ZF is protons minus core electrons. So for example, with boron, we have 5 protons minus 2 core electrons. That's a pull of +3 that these valence electrons are feeling. Over here with oxygen, it's number 8. So we have 8 protons, and there's only shielding of 2 electrons again in the core. And so it's 8 minus 2, and so these are feeling a +6 pull. And so as you go across, you're going to get smaller and smaller and smaller as that ZF, that effective nuclear charge, changes. If you get on to row 3, same thing. In row 3, they all have 2 in the first shell, 8 in the second shell, and so you have 10 core electrons. And that will happen all the way across the third row. So again, going across the third row, 10 core electrons, so the same thing happens. You're adding a proton, and you have the same shielding, so ZF increases. Okay? So that's why we see these numbers increase as we go across. When we talk about the size of an atom, we use this word atomic radius. And you have to remember, an atom isn't like this little solid ball. It's very, very small. It's a solid nucleus, but then around it, it's just a cloud of electrons sort of spinning around it, like bugs zooming around a light at nighttime. And so they're sort of just swarming around it. There's no outside edge, though. There's no solid outside. So we can't really measure an outside perimeter. And so the best way to figure out the size of an atom is to look at a diatomic version of it, like H2 or O2 or Cl2. And you just measure halfway between the nucleus of both of them, and we call that atomic radius. So that's sort of how we can figure out where this outside edge is. It would just be halfway between the nucleus of a diatomic atom, so 2 of itself. And there's not a really easy way to measure these. So ZF, again, affects size. If you're looking at chlorine and magnesium here, it's a European spelling of magnesium, I guess. Chlorine, number 17, row 3, so it has 10 core electrons, giving it a +7 charge. And magnesium, only 12 protons, but it's larger than chlorine because there's 10 shielding, So 12 protons minus the 10 shielding that are inside here, the core, gives us only a +2 field that these outer valence electrons are experiencing. And so when these are only feeling a +2 pull, they can drift out a little bit and they don't get pulled in as tight. These valence electrons are feeling a +7 pull. That's a strong pull from the nucleus. And so they get pulled in a little bit tighter. And that's what makes an atom have different sizes. It has to do with the pull, the protons in the nucleus, and the amount of shielding electrons that it has. It's two things involved every time. This just sort of summarizes it, this slide. I just put this on here for you to revisit if you need. Basic patterns. Again, as you go left to right on the periodic table, ZF increases, so size decreases. And as you go from top to bottom, you're adding a new shell every time you get a new row. And so you're going to increase in size. And every time you add a new shell, those valence electrons are getting farther and farther and farther away from the nucleus. And so they're feeling less of the pull of the nucleus as you get further from it. And as a result, it allows them to spread out a little bit even further. And so as you go down a column on the periodic table, you're going to increase in size. And again, that's because you're adding, as you go down here, you're adding a new shell every time. So here we see 2 shells, here we have 3 shells, and then 4 shells and so forth. So again, another summary of atomic radius here and a visual of it so you can sort of see what it looks like. So again, as we go left to right, we're decreasing in size all the way across. And as we go top to bottom, we're increasing in size. We do have more protons as we go down, and that sort of helps keep things in check and make sure that the electrons aren't totally drifting away. So cesium obviously has a lot more protons, but those valence electrons are further out, and so it doesn't get too big. So it sort of increases nicely in size. Then we have ions, and ions are where it gets a little bit tricky because you really have to think about ZF again. So remember, cations have positive charges, and they're smaller than the atom they come from, but why? So why is, for example, lithium here, Li, bigger than lithium +1 down here at the bottom? They have the same number of protons. That's never going to change. Both of them have 3 protons. But remember, a +1 charge means you lost 1 electron. So Li +1 only has 2 electrons. And it does that to be like a noble gas. And so it actually has a noble gas configuration. It looks just like helium does. Helium's number 2 on the periodic table. It's a noble gas. It's stable because it has this first full shell, fully filled with 2 electrons. And so if we were to find the ZF of these, lithium, 3 total protons minus the 2 core gives it +1. But Li plus here, it doesn't have any core electrons anymore. Once it lost this 1 valence electron, now it only has 1 shell, and it has nothing protecting those 2 valence electrons from the nucleus. And so its overall ZF is 3 protons, no core, it feels a +3 charge. So this is going to be substantially smaller as an ion than as a neutral atom. With anions, remember, nonmetals gain electrons, and they gain electrons, again, to be like a noble gas. Their ion is going to be bigger than the neutral atom, and we can look at those again. Here's oxygen, and here's oxygen when it gains 2 electrons. So both still have the same number of protons, 8 protons, 8 protons. And oxygen needs 2 electrons to be stable like a noble gas. And so it gains them and it puts them right here in this outer shell, in shell 2. And now it has 8 outside. But it still has 2 shielding electrons. That never changed. All it did was fill up its second shell. its first shell still has 2 core that are doing shielding. And so our ZF is still going to be +6 for both of these. 8 protons minus 2 core. So the reason this is a little bit bigger is in oxygen, you have the 8 protons pooling on only 8 electrons total, or a total of 6 valence electrons. But now over here, you start to add more electrons. And so it's like, I don't know what a really good example is here, but these protons are now starting to get, they're losing their ability to pool a little bit because there's more and more and more electrons. And the more electrons there are, they can't pool on all of them. And so it gets a little bit harder. Imagine if you're walking your dog. It's easy to walk one dog. If you're walking 5 dogs, those 5 dogs are, if you're the nucleus pulling those dogs on the leash, the more dogs there are, the less pull you're able to pull on all of the different leashes. And so eventually you're not going to be able to walk all the dogs. They're just going to have their way with you. So that's like the nucleus and the valence electrons. The more valence electrons there are, the less the nucleus can pull on them. And so as a result, since that pull is being spread out, the anion expands. And you're getting a little bit of repulsion also from these electrons, and these electrons, and these electrons, and these electrons, and they're repelling each other outward as well. So that's anions and cations. So for cations, they're always going to be smaller than their neutral. For anions, they're always going to be bigger. Okay. And we can look at a visual of this. So the ions are in gray. So if you look at all the metals here, the metals are obviously everything with a plus charge here. And so the gray dot is the size of the ion. The lightish blue or the grayer blue outside is the size of the neutral atom. So you can see the ions are smaller. This is Ca plus 2, and then this would just be Ca. Okay? So as soon as you lose those electrons, it makes you get smaller. And part of that reason is that you lose a shell for these as well. For the nonmetals, again, the dark gray is the ion, and the tan is the neutral atom. So for example, phosphorus is this size, phosphorus minus 3 is this size. And that's because you added extra electrons on there, same number of protons, same shielding, and so the extra electrons allow it to drift out a little bit. So let me unmute everybody. Questions on some of that?
My eyes hurt. But
Eyes.
so basically when you lose electrons, that basically makes it smaller, and when it gains electrons, it makes it bigger.
Yes, and you have to always be able to explain it in terms of effective nuclear charge or in terms of electron repulsion. For these, you would just say the nucleus, the effective nuclear charge is lessened. Those valence electrons are feeling less pull because you're feeling, you added valence electrons for the nonmetals, and that pull from the nucleus is being spread out more and more and more because you added more and more valence electrons. For the metals, you lost valence electrons, and so same number of protons, and so it's pulling a little bit tighter now. ZF increased substantially. Does that sort of make sense?
Mm-hmm.
Yeah. Any questions on it? All right. I did want to go over configurations of ions because there were some issues with that. So if we look at like sodium, 1s2, 2s2, 2p6, 3s1, it's number 11, 2, 4, 10, 11. But when it makes an ion, remember, a positive charge means it did what? Lost an electron,
It
right?
lost an electron.
And so it loses this one. It loses its valence electron. Na has how many valence electrons? Remember, you find the highest shell, And so let me annotate here. So you find the highest shell. So our shells are 1, 2, 2, and 3. You count the electrons on the highest shell, and that's your valence electrons. That's why Na is in 1A, because it has one valence electron. But when it loses that valence electron to form an ion, how many valence electrons does it have now?
Has
8, like a noble gas. So remember, they always form ions to be a noble gas. The highest shell is now 2. So we add them together. 2 plus the 6 gives us a total of
8.
8 valence electrons, which is a noble gas. So this is a noble gas configuration, and this is neon, 2, 4, 10. This is neon's configuration, and that's why we say they try to get a noble gas configuration, because Na plus has the exact same configuration as neon, 10 valence electrons. So on the periodic table, the metals are always going to go backwards towards the noble gas, and non-metals will always go forward to become that noble gas. So Ca plus 2, K plus 1, and Ar are all going to have the same number of electrons. And we can go back and look at that here. K plus means it did what?
You lost the electron.
Lost one. So it lost one and became like which element? Sorry.
AR.
Yeah, it became like Ar here. Ca lost 2 electrons and became like
AR.
Ar. Sulfur gained 2 to become like,
AR.
and chlorine gained 1 to become like Ar. So if we do the configurations of these ions, sulfur minus 2, Cl minus 1, phosphorus minus 3, K plus 1, Ca plus 2, they all have the exact same configuration. They all have the same configuration as argon. Okay. So everyone has the same exact electron configuration. And because of that, we have a name for that. It's called isoelectronic. The prefix iso means same, and electron that refers to electrons. Again, all of these would all have the same configuration as neon. So these are all isoelectronic. We could look at their size though, and that's going to be different. Who would be the smallest out of all these?
AL plus 3.
Good. Al plus 3 would be the smallest. It's going to be the one that lost the most electrons and still have a large number of protons, giving it a high effective nuclear charge. So these are going to be the smallest. So Al first is smallest. Mg is a little bit bigger. Na is a little bit bigger. Neon's a little bit bigger. And then who's the biggest out of these two?
O minus 2.
O minus 2, yeah. It gained 2 electrons, and that allows it to drift out a little bit. And so that's a common multiple choice question on AP. There's the effective nuclear charges of all of them, just so you can see it. Al is a plus 11, so that's a really strong pool. It's going to make it really small, whereas O only has a plus 6, and it has extra electrons. Another visual of them, the pink is the ion size, the gray is the neutral. And for the nonmetals, the blue is the ion size, O minus 2, and the gray is the nonmetal, neutral atom. Okay. So I'm going to introduce our new topic here. This is one of the most tested concepts in AP, and it's based off what we did, and it's the only new thing we're doing today, and then we'll just do some practice problems. So this will take a couple minutes, but it shouldn't be very long. It's not that tough of a concept. So I'm going to mute again and Back to it then. Right. So ionization energy is the energy required to remove an electron from an atom. And so you're going to have numerical values for these. And it's generally given in kilojoules per mole. And that's how many kilojoules of energy are required to remove 1 mole of electrons from these. Don't worry about that. You can think of it just as 1 for our sakes. So we always, when we remove electrons, we're always removing a valence electron first. So if I were to draw lithium real quick here, and just sort of look at what a lithium atom looks like. So we have our nucleus for lithium. Lithium's number 3. So we have our first shell, and that gets 2 on it. And then we have 1 on the outside, right? Just gonna make our nucleus look a little bit better. Okay, so this is lithium. Ionization energy is the energy required to remove the outermost electron, that one right there. If there's 5 valence electrons, it doesn't matter which one. It just means the energy required to remove 1 of those 5. If there's 8 valence electrons, the energy required to remove 1 of those 8. But here, since lithium only has 1 valence, it's always going to remove that outer one first. And so obviously we have a ZF. We have the nucleus pulling on that electron. And so if you want to remove that electron and pull it off of there, it's going to take some energy to remove it. But at the same time, metals sort of want to get rid of that electron so that they can become stable. So it's going to take some energy, but it's not a whole lot. And so we can see on our next slide. Of course, I don't have lithium, but it's going to be a small amount of energy required to remove that first one. That's not that bad. The problem comes in when you now need to remove the second one. And so if we're removing that second one, and I wonder if I can redo it and put it back. Sorry, I shouldn't have not have cleared that. This is going to be bootlegging quick. So again, we removed our outer electron. Now we only have 2. It's going to be really, really hard to remove this. This is a noble gas configuration. This is stable, and you have no shielding electrons now. So if you want to remove an electron off of a full shell, remember shell 1 holds 2 electrons, it's going to take a huge amount of energy now to remove that. And so after you sort of remove electrons from the valence shell and you start to try to remove them from a full shell, you see this huge increase in energy required to do that. So let's look. So Na has 1 valence electron. Here's the amount of energy required to remove its 1 valence electron on the outside. But look at the jump then from here to here. You have this huge increase of over 4,000 kilojoules of energy to remove it. And that's because now you're trying to remove one from a full shell. Na again has 1 valence, and after you remove it, now it has a full shell. So the second ionization energy, I1 means the first one, the energy required to remove the first electron. This is now the energy required to move the second, the energy to remove the third, the fourth, the fifth. And we can predict what an element is from looking at these ionization energies. For example, Na we know as 1 valence electron because the first electron doesn't require much energy, but now the second one does. That tells us this is something in family 1A that has 1 valence electron. Magnesium, here's the energy required to remove the first valence electron. Bigger. The second one, to remove the second valence electron on its outer shell, it's a little bit stronger, and it's going to be bigger because, again, ZF just increased. You have the same protons, but you removed an electron, so that 1 electron that's left is feeling a stronger pull. There's not electron-electron repulsion going on that outer shell anymore. And again, I think it's helpful maybe if we, no, actually I think I have this on the next slide. I do. So again, looking at magnesium and sodium. Sodium has this one valence. You can remove it, but now you're dealing with a full shell. It's really, really hard to remove from a full shell. So you're going to see a huge jump in energy after you remove the first one to try and remove a second one. Magnesium, you remove the first one, it's definitely going to take more energy to remove a second one, but then you're going to see a huge jump in energy to remove a third one because the third one would be coming off of this shell. For aluminum, again, same thing. First one takes some energy, more energy for the second, more energy for the third, but then you're going to see a huge jump to try to remove from a full shell. And if we go back and look at those numbers for aluminum, first valence electron, pretty big. Second one, bigger. Third one, bigger. But then we have a huge jump of over 9,000 going between the third and the fourth ionization. And again, that's because that fourth one is removing the fourth electron, one from this shell. And that's a full shell, and it's stable, and it does not want to give up those electrons. And so what you do in these problems is you always look where the jump occurs. Where do you see a massive increase? And that's going to help you figure out how many valence electrons it has. Because the valence electrons are all pretty similar in number. Once they're all removed, you see a huge jump. So for example, we know silicon has 4 valence electrons. 1, 2, 3, 4. Once those 4 are gone, now you see a huge jump of over 12,000 because now we're removing an inner electron from a new shell, and that's a stable shell. And so we can just predict, basically, always just look for the big jump, and it'll help you figure out where or what family it's in or how many valence electrons it has. For example, here's the ionization energies for element X. We don't know what element X is. So let's take a second and I'll unmute and we'll see if we can solve this one.
And after that, let it boil.
Yeah. So where do we see the jump? Between the first and the second, second and third, third and
The
fourth,
third and the fourth.
and fifth.
Third and fourth.
Third and the fourth.
Third and fourth, right? This is only 5, like, I don't know, 1,300. This is like 900. This is 9,000. And this is like 3,000. So here's your jump. How many valence electrons does element X have?
Element X, 1, 2, 3.
3. Good. The first one's not too hard to remove. The second one's not too hard to remove. The third one's not too hard to remove. But after you remove those 3 valence electrons, now you're at a new shell on the inside. So which element has 3 valence electrons here?
Yeah.
Al.
Yeah.
Good. We can go backwards and we can go back and see that Al is in family 3 and it has 3 valence electrons. So that's how the AP test sort of tests your knowledge on these. That's a simpler one. Again, where do we see the jump in this problem?
Third and fourth.
Yeah, between the third and fourth. How many valence electrons would this element have?
Also
3.
3.
3.
So our options are it's either boron or it's nitrogen. So let's go back to the periodic table and rule one of those out. Who has 3 valence electrons? Boron
Boron.
or nitrogen?
Boron.
Definitely boron, right? So we just ruled out half our answers.
Mm-hmm.
So we know that it's going to be boron. And why is it boron? Is it boron because it has 5 core electrons or boron because it has 3 valence electrons?
Because it has 3 valence
Yeah,
electrons.
it's the valence electrons that are being removed. In fact, if we go back, boron doesn't even have 5 core electrons. It only has 2 core electrons. So that statement's just entirely wrong. And so ionization energy questions are everywhere on the periodic table. Sorry, on the AP test. But use your periodic table, and you can always sort of figure them out. Always look for the jump. The ones that are lower energy are your valence electrons. Then this now is one of the core electrons.
So basically, you just count till the jump, and that pretty much just tells you how many valence it has.
Exactly. Exactly.
Okay, then.
Okay. Simple.
By definition, it's the energy required from a gas or an ion. I don't care about that. Just looking, you can see it goes up. And as it goes up for magnesium, the magnesium plus 1, the magnesium plus 2, every time it loses an electron, it's going to increase in ionization because, again, you have a stronger pull of the nucleus every time. Plus 1, plus 2, plus 3. So your basic patterns are ionization energy increases from left to right, and you have a higher ZF as you go from left to right. And again, it's all because of shielding and effective nuclear charge. Every time that you are removing an electron, you still have the same number of protons. So when you're stealing one single element, every time you remove an electron, ZF gets stronger because you're pulling on less electrons. As you go from left to right on the periodic table, you're adding a proton every time, and that proton just pulls harder and harder and harder. So the last thing I want to talk about today is the weird exceptions we get. And one of the weird exceptions to this, the first ionization energy of phosphorus is 1060, and for sulfur it's 1005. And we wouldn't predict that that would be the case, because when we go back, here's phosphorus and sulfur. And we said ionization energy increases going from left to right, but between all of these, there's actually a little decrease. And we have to figure out why that is. And the reason for it has to do with
What? Yo, can you get out? Oh my God, Dugan, can you
This is-
mute me?
I am. I'm muting now. All right. So let's go back here. So why? Why is phosphorus higher than sulfur, even though it comes before sulfur? And we have to look at sort of the orbital diagrams for this. Remember, these are just electron configurations. Phosphorus is number 15, sulfur is number 16. So 2, 4, 6, 8, 10, 12, 13, 14, 15. This is going back to Hund's rule, again, which we talked about earlier. The first electron up, second electron down. And by having these opposite spins, it minimizes repulsion. So you first do 1s, then you put 2 electrons in 2s, and then you put 6 electrons in 2p. So remember, the way we fill them is always up, up, up for the first 3, 4th, 5th, 6th. So you go up, 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 down, down, down. And you do that because electrons don't want to be near each other. They repel each other. So 3s up, and then 3s down. 3p, up, up, up. So looking at phosphorus and sulfur, the reason that sulfur is actually a little bit, has a slightly lower first ionization energy is because when you put that next electron, so this is 15, up, 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 and this is 16, up, 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 and that next electron goes down, these two start to repel each other and expand a little bit, and so they're a little bit further from the nucleus than phosphorus is. So they feel a little bit less pull, and so they're a little further from the nucleus, and so it's a little bit easier to remove one from sulfur than it is from phosphorus. And then it goes back to the normal pattern. So every time you're on the periodic table, you always get this little jump from here because it's always goes up, 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 and then this is the first one that goes down. Up, 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 and then sulfur is the first one that goes down. So between here and here you have orbitals all with one electron. Now you have an orbital that has 2 electrons in it. Same with oxygen, same with selenium, same with tellurium. You also see a little bit of a jump sometimes from S to P, and that's because from here to here, you're going from a full shell, 1s2 is fully filled, and so now you're in the next shell. It's a little bit easier to remove this one than from a full shell. So you see a little bit in dip from here to here also, and from here to here. But then it, again, tends to increase, increase. Small dip, increase, increase. So it's a little bit weird. The book does a pretty good job of explaining it. And it's just about those valence electrons and how they're sort of being shared in an orbital together. And so this is an example of a problem that tests this. Table shows the first ionization energy and radius of several elements. Which of the following best helps explain the deviation in the first ionization energy of oxygen from the overall trend? So again, we're going right across row 2. So B, C, N. We're just continuing right across. O, F, and NA, NE. And we see it's increase, increase, decrease, increase, increase. So why do we get this little decrease again? Again, it has to do with the fact that when you're dealing with oxygen, it's up, up, up with those valence electrons. And now oxygen is the first one to have one down in the 2p. So it looks something like this. So in oxygen's 2p, so we can just do it. We can do the whole thing here. So going for oxygen, oxygen is number 8. So so 1s, 1 up, 1 down. 2s, 1 up, 1 down. Now we're in 2p. 2p up. So this is 2, 4, 5 electrons. Remember, oxygen has 8. So it's 5, 6, 7, 2, 4, 5, 6, 7, and then down 8. And again, these two start to repel each other. And as a result, that causes the atom to expand a little bit. These electrons are further from the nucleus. And so because they're further from the nucleus, they're feeling less pull from the nucleus. And as a result, if you go in and you try to remove an electron that's now a little bit further from the nucleus, it takes a little bit less energy than if it were closer to the nucleus. And so that happens every time you have a jump. You can have a small dip from here to here, here to here, here to here, here to here, and here to here. So you get these little tiny dips every single time that you're going to do that. And that is all I really wanted to go over in terms of new content today. So let me see if I can unmute. I gotta stop annotating, sorry. Still getting used to this.